Hello, friends. IVF Worldwide has the pleasure to host today Dr. Sherman Silber, who is a pioneer in microsurgery and infertility and being considered a leading authority on IVF, sperm retrieval, ICSI, vasectomy reversal, tubal ligation reversal, egg and embryo freezing, testicular and ovary freezing, and ovarian tissue transplantation. Also, he was the first to introduce ICSI to the United States, as well as rectification. Dr. Sherman performed the world's first microsurgical vasectomy reversal, as well as the first testicular transplant in the 70s, and now, in the current century, the world's first ovary transplant. He was the first to develop the TESA and MESA techniques for retrieval testicular and epidermal sperm in azoospermic men. He headed the clinical MIT team that first mapped the sequence of the Y chromosome in infertile men. Most recently, he has perfected the preservation of fertility for cancer patients with ovarian freezing and transplantation, and thereby figure out how to extend the reproductive biology clock of women. He is the clinical director of the only IRB in the world to study the transformation of human skin cells into iPS cells, and from there into germ cells, oocytes, and sperm. He is the author of 3 medical textbooks and more than 200 scientific papers on human infertility and reproduction. Dr. Sherman present today is about ovary freezing with non-stimulated egg retrieval and IVM. Dr. Sherman, please.
Thank you very much for that kind introduction, Zev, and it's really an honor to do this, and I think this is the wave of the future with our fear and our management of the coronavirus epidemic around the world. We're going to be finding that it's easier to have more and more of these, so to speak, virtual conferences. So I would like to talk today about ovary transplants, but really freezing ovary tissue to preserve fertility for cancer patients. But something that's very, very special now, and I can't claim originality for it. I got this from Klaus Anderson, but it is very easy now at the same time to retrieve many eggs from this ovary tissue at the time of the dissection and to convert them into good M2 oocytes with a relatively simple IVM technique. So I will tell you that I have too many slides. So bear with me when for the half hour I'm presenting, from time to time, I will skip ahead so that I cover all the subjects. And so I will stick within the half an hour, even though the slides would normally go way over that. Now, the first slide just shows how we quilt together this ovary tissue that's been thawed before we transplant it back. I want to make sure that I'm going to, how do I escape? Sorry, this, yeah. Okay, sorry, I'll go right back to here. And you see we transplant this frozen thawed tissue in a place where the fallopian tube can reach the surface of where ovulation occurs. So all of our pregnancies so far with frozen ovary tissue have been spontaneous from orthotopic transplants. But by the end of this lecture, you'll know we don't have to rely on that. We can also get metaphase 2 eggs with in vitro maturation that will be good for IVF for these patients also. So just ordered to summarize quickly ahead of time, just in case we don't get to it. Our results just in St. Louis with ovary transplantations with our series are that we have 27 healthy babies. Now, it's true that 9 of those cases were from fresh transplants with identical twins, but 15 were from frozen transplants. And the success rate is certainly over 75% in terms of live baby. And if you look at the bottom, you'll see that 3 out of 5 cases were from vitrified ovary tissue and 14 from 10 slow freeze. And so the success rate seems to be the same, whether it's slow freeze or vitrification of ovary tissue. Around the world, there's now over 183 documented pregnancies from frozen ovary tissue. So ASRM no longer considers this to be experimental, although we fought for 25 years to overcome this designation as experimental. This is a very busy slide, which you don't have to do now. I can always send this to you and talk to you about it. But if you look on the right, you can see most of these frozen ovary transplants are still functioning, even though it's only a few pieces of ovary tissue. So this tells us not only that this is a robust procedure, but maybe more importantly, helps us understand better the mechanism of longevity of the ovary, so that we could actually have ovary function for 50 or 100 years if we take advantage of the fact that the lower the ovarian reserve, the slower the rate of primordial follicle recruitment. And I'll explain to you why, because we really have been able to study in the deepest way ever before the otherwise mysterious physiology of the ovary, just on the basis of these cases. And you can see we've had leukemia patients. We already have 6 babies from leukemia patients with no transfer of leukemic cells. But even so, from now on, we will have M2 oocytes via IVM for patients in whom you're concerned about doing the transplant. You can see here the summary of the leukemia cases, and now we actually have 5 babies and another one on the way from 2 leukemia patients. And so let's just talk about the subject: ovary freezing, transplantation, ovarian longevity. Oh, sorry, I shouldn't have put that in. It looks a little arrogant, but that's me, in case you haven't seen me at the meetings. And I'd like you to hear this interview with the first leukemia patient.
There's never been any doubt in my mind that I wouldn't be cured of this. Once I found out, I just made up my mind. That's it. You just have to keep taking it one day at a time, and just keep that positive attitude and know that I can do this. I'll get through it.
It's 8 o'clock in the morning, July 17th, 1997. We're at St. Luke's Hospital, and we're about to do the first case in the St. Louis area of ovarian tissue freezing. This is very dramatic.
Okay, well, I'm Dr. Silber, German Silber, the Infertility Center, St. Louis, and we really have a treat right now. This is Jennifer, who at 24 years of age, I'm right on that, yes, came down with a terrible case of leukemia. They thought she was going to die, but just to be safe, in case she lived, when she did, and was cured, we would freeze her ovarian tissue. So that was like 20 years ago. And this is the first case that we ever did, and we're the only ones right now really actively with the program in the whole United States. And it's been a long time, and we didn't know that we'd be able to transplant the tissue back, and we didn't know if we could culture the tissue. And here she is now. We had her on Facebook Live several months ago, and she was happily pregnant, and now look what we have. Now she's 44 years old, if I can reveal that, with a 24-year-old ovary, and beautiful baby. What's her name again?
Madeline Grace.
Madeline Grace.
Another dramatic case coming up. This is our second ovary freeze patient from 1997. She's now 39 years old.
Silber, Infertility Center of St. Louis, and I'm here with the most amazing fertility story ever. This is Amy Tucker. I've known her since she was a little 19-year-old girl who was facing death with Hodgkin's disease, a terribly difficult case. And she's got 2 children from her frozen ovary that we froze before she underwent her chemo and bone marrow transplant that sterilized her. And
I'm going to skip ahead because of time to just a third dramatic case. I want to point out this really works.
We couldn't have children. Really scared and frightened me.
2 years ago, at the age of 21, Melissa was diagnosed with Hodgkin's lymphoma. She was told her treatment would include very high doses of chemotherapy.
I thought, I'm young, I can do it.
The odds are looking really great for me. Hodgkin's lymphoma, very curable. And then I really started looking into my papers and my books that you get, and I came across fertility, and I burst into tears. I don't have a biological clock anymore. He took it away from me. So when I'm ready to have kids, it's not going to be a problem.
13 years later.
Well, Melissa, this is a fantastic moment for all of us.
It is.
I mean, when are you going to have the baby?
We are scheduled for a week from yesterday, so six more days.
6 more days, and you look really ripe.
I am very ripe, yes.
And that's her baby. And I'd like to talk now about the mechanism of all this, and I will skip some slides in order to really get to the meat of it. But the first part of the lecture you've already seen. I want to make a strong emotional point. The data is there. It's over a 75% success rate with spontaneous live babies, and it should never have been considered experimental over at least the last 15 years. For whatever crazy reason, we're the only series in the United States doing it. We've been led in this by very good programs in Israel and in Denmark and in Belgium. But in the United States, we're the only ones that have done this, and it kept on being considered experimental. No longer is. From 1997 to the present, 23 years, when we didn't know if it was going to work, and now look at this as clinically very robust. So now let's get into the science and what else we're learning about it. First place, the germ cells all begin in this tiny packet of cells in the early epiblast. And we're going to show you in the next lecture when that really happens in the human. This, of course, is the mouse, but it's remarkably similar in the human. These cells have to be separated from the rest of the developing body because these cells remain pluripotent, and these cells are the eternal cells that keep us as a species alive forever. And they migrate, as you know, towards the 3rd week to the 6th week of fetal life to the dorsal ridge, where these germ cells PGCs will enter either the testes or the ovary, depending on whether it's a male or a female. Now, we found that the intrinsic fertility of the human oocyte drops very, very readily from the late teens to the early 30s. And then around the age 35, there's just a very dramatic fall. And that's because we know that the oocytes do not have stem cells, despite the controversy. We don't see any evidence of stem cells, despite looking and looking and looking. And so the oocytes basically run out and they get old. I'm going to talk in this lecture and the next lecture a little bit about how they get old. But there's no question, based on 14,000 cycles of single embryo transfer natural cycle, when we can look at the intrinsic fertility of each oocyte, we can see the gradual decline that occurs from the teen years into age 35 and the 40s. And we can even see that it's similar if we have minimal stimulation. If we have maximal stimulation, then we wind up retrieving a lot of poor quality eggs from the ovary during the stimulation cycle that don't help in the success rate. And the problem that many patients suffer is they're afraid to remove all of their one ovary, but it makes perfect sense to remove all of their ovary. I'll explain to you why in a minute. But if we were to do IVF by stimulating the cycles, Cobo et al. Showed that you'd need 40 frozen oocytes to have a 97% success rate, or 30 to have an 84% success rate. And if you overstimulate the patient, you will need more than those 30 oocytes because you have so many bad quality oocytes. So with mild stimulation, you would need 3 cycles, which the cancer patient doesn't have time for. Now, let's look at a Japan series of 24,000 women, their natural age of menopause, which of course varies, but averages at about age 50 or 51 in every racial and ethnic group on the planet. Look what happens if they had one of their ovaries removed when they were young. It doesn't make a significant difference in the age to menopause, which is one way of demonstrating that the lower the ovarian reserve, the slower the recruitment of primordial follicles, and therefore the longer the longevity of the remaining ovary tissue. And this was first published by Hamish Wallace, but verified by that a huge 24,000 person Japanese study, by replacing one single piece of cortex, the recruitment rate will constantly be very low. Utilization of follicles will be augmented compared to what's natural. And theoretically, if you transplanted one or two pieces of ovary tissue, we found that these last for anywhere from 6 to 8 years. And you might have the possibility of 6 such transplantations. So you would have enormous longevity from that one single ovary. Now, biologically, what's interesting is that as the FSH comes down over 4.5 months after the transplant, the AMH goes up to dramatically higher levels. There is a huge over-recruitment of follicles 4.5 months earlier, represented by the AMH when the FSH comes down. And then, despite a very low AMH, these tiny pieces of ovary tissue last for anywhere from really 4 to 8 years, even though it's a tiny piece of tissue. So this tells us something about ovary longevity and what controls this so-called mysterious mechanism of ovary follicle recruitment. So these are our ovary tissue transplants. You see that all of the primordial follicles are located in the outer cortex, this dense tissue. And what we found now, although this is an old slide, but if you look closely at it, you can see that the follicles begin to develop not toward the outside where they ovulate, but towards the softer inside. The most dense tissue is on the outside, right on the edge of the epithelial lining of the cortex, and the least dense tissue of the cortex is on the inside, and then goes to the corticomedullary junction where the follicles actually develop over about 4.5 months. And that's how we discovered this from ovary transplantation studies. Then, once it becomes a big Graafian follicle and ovulates, it explodes towards the surface and explodes out the epithelial surface, but it doesn't develop towards the epithelium. It develops based on a tissue pressure gradient. That simple. This is another view showing the same thing. And then if you just shave off the outer cortex, you will have all of those primordial follicles, and you can easily freeze this tissue and transplant this tissue because everything that's important in the primordial follicles are located in this outer millimeter. That's what the same thing looks like when you actually surgically dissect it. Now, one way of preparing the tissue is the method of Masa Kuyama. We've done that for a long time, just shaving off cortical tissue slices so that we have thin tissue.
We begin to resect thin 1 millimeter.
I'm going to skip that just because I don't have the time, but this is the way we used to do it. And we used a template and made these very thin pieces of tissue, and they worked extremely well, whether by slow freeze or vitrification. We know vitrification does no damage, and slow freeze damages about 50% of the ovary cortex tissue. But that doesn't make any clinical difference, we found, because, you know, if you have 100,000 oocytes and you reduce it to 50,000 by slow freeze, it's not going to make any clinical difference for the reasons I've already discussed in this lecture. So the only reason for doing vitrification, which we prefer, is that it's easier and requires no machinery, and you can do it simply and quickly. But I'm not advocating it as being more efficacious. Now, I could go through the whole formulation for a vitrification solution, but I'll summarize just by saying instead of using 15% cryoprotectant for ES solution and then 15% for EG solution, we use 20% ethylene glycol and DMSO. So the total would be that it would be 15% total cryoprotectant for just equilibration, but actually 40% cryoprotectant for the vitrification solution. And we can tell that it's all been completely absorbed when they all fall to the bottom of the test tube. And that's the only test that you need to know you've had good absorption. There's no difficult timing problem with tissue. And then you just put it on a grid and you dry the tissue off so that you have a maximum freeze rate or cooling rate. And then you can do closed storage of it in liquid nitrogen tanks. And for thaw, for vitrification, similar, we use 40 cc's of 1.0 molar sucrose and for a minute, and then we go to dilution solution, 0.5 molar sucrose, and that's a very, very simple procedure. This is what the tissue looks like before you froze it. This is what it looks like after vitrification. Nobody can tell the difference. And with viability studies, we see that we have the same number of viable oocytes with vitrified as with fresh control, whereas we lose about half of them with slow freeze. Doesn't make a clinical difference. And this is what I showed you earlier. After the thaw, we quilt the pieces of tissue together, and we do think a meticulous transplant technique is important to get the best results. We've seen terrible transplant techniques, really clumsy, terrible stuff. And of course, you're not going to get the same results then. We want to use a really beautiful microsurgical technique so that there's no adhesions. And so whenever ovulation occurs, the fallopian tube can pick it up well without any resistance to being picked up by the fallopian tube. There you can see us putting it in place over the denuded cortex, again using 9-0 nylon so that there are no adhesions, continuous irrigation with heparinized saline. And I'll skip through this quickly, and you can see, like you saw before, we rely on the fallopian tube to pick up the egg upon ovulation because IVF with these cases is very difficult, and natural pregnancy is the preferred method for both Anderson and the preceding people in Belgium, and for us. IVF can be done, but it's tricky, and natural conception is better. But I'm going to change that a little bit because now, using Klaus Anderson's technique, we can do IVM and get M2 oocytes also. Now, we know from fresh and frozen how long it takes from a primordial follicle to reach the gonadotropin sensitive stage. It's a 4-month, 5-month period once the follicle is recruited, and we got that definitive evidence in the human from these ovary transplants. And you've seen already that remarkably, after 4.5 months, when the FSH comes down to normal, the AMH goes sky high, indicating a massive over-recruitment at the time of the transplant. And if we put that all into one big statistical graph, we can see that this is very consistent for all of our cases. And again, like I've said before, we have 27 healthy babies now from this technique, and around the world there's 183. I'll skip through these that I've already mentioned. And the benefit of our tissue freeze for cancer patients versus eggs is less time to wait before cancer treatment. No problem if chemotherapy has already begun because we're getting the follicles, the resting follicles that are more resistant to chemo. Even though the developing follicles are dead, it's 1/10 the cost, less troublesome than going through overstimulation, and we can get return of hormone function as well as fertility of the eggs. No problem if chemotherapy has already begun, as you can see, because although some cortical follicles are destroyed and all the developing follicles are destroyed, many cortical follicles remain. And so even if they've begun their chemo, taking out the ovary is the only alternative for ovary tissue freezing. This is what the tissue looked like after full chemo and bone marrow transplant, but we still had a lot of eggs from her previous frozen tissue. So now what I'd like to do after this summary is to go ahead to IVM. So I'm going to escape, okay, and go all the way down to IVM. I've got all kinds of interesting things here, ovary tissue longevity and rotation, but I'm going to go for the next 5 minutes. So you'll invite me for another talk in which I can talk about the mechanism for primordial follicle recruitment and arrest based on rotation of the nuclei. But right now I want to talk about something brand new, IVM, that is very exciting. So this is an example of the first case we did with Klaus Anderson's direction. This is a patient with a B-cell lymphoma, and she was ready to start chemo right away. So we went with ovary tissue cryopreservation, but we also did the dissection by hand the way we did it in the old days. And we wound up with 23 eggs, which is the usual. And we got from those 12 beautiful M2 oocytes. So I'm just going to show you a little bit how we do it. First, we dissect the ovary, and we use the technique we started by Roger Gosden in 1997, the technique that Jorah May Rowe uses now and shows so well. And we just make a cut, longitudinal cut from stem to stern in the cortex of the removed ovary. And then we just free it up as, and I'll show you a video of this as we free, a very brief video, how we dissect it out. And there's going to be media in that dish. And as we do the dissection, there's going to be a lot of automatically broken antral follicles, and GV oocytes are just going to naturally fall out. And they're going to fall out into that media that you see. And you can use almost any kind of media. Let me show you this dissection a little further. We dissect the medial out so that we have just a thin piece of cortex, and we pay no attention except we make sure there's always media in the dish. And lo and behold, when we're done with that, and I'm sure many of you have observed this, there will be many, many GV oocytes in the media. So we just dissect it out, and that's just a picture. And if you look at that media, you can't tell, but put it under your dissecting scope, and you will find many, many GV oocytes with a tight granulosa cell, cuboidal cells around it. And so now we're continuing to thin out the media, to thin out the tissue, and we make all these different pieces of tissue that are so thin we can safely vitrify them. We could slow freeze too, but we prefer to vitrify. And then if you look at them in the dish, you can see almost like stem cell cultures. There's a plating out that occurs, and that plating out will have a lot of GV oocytes. So the histology shows many primordial follicles as well as these developing follicles. And you can see the developing follicles, just beautiful. But now just look at it in the Petri dish. We have 23 of these in the first case, and usually we get more than 20. In a tight cumulative cell package, they're obviously GV oocytes, many of them. It's amazing how many of them are. And then we just culture them for 36 to 48 or more hours, and lo and behold, they're M2s, and they look like beautiful M2s. And about half, a little bit less than half, some will be atretic like the one on top, and some will just be M1s like the one on the right. But you can see of these 5 oocytes at 36 hours, 3 of them are beautiful M2 oocytes. And here's actually 3 out of 3 M2 oocytes. What is the media? The media is very simple. Use Medicult or Sage, any IVM media. I'm not sure how important the specific media is. Just or your usual ordinary culture media, in fact, and make sure you have human serum albumin, 10 milligrams per milliliter. Now, we find the simplest way. I'm not trying to sell Menopure. In fact, I don't even like that product, but I'm not trying to sell it. But what you would like is 75 to 150 milli-IU per milliliter of HCG and 75 milli-IU per milliliter of FSH. It's really that simple. It's remarkably how fast it develops. So at this point, I could summarize in the minute that I have left before we answer questions that ovary freezing is an extremely robust method for preserving fertility for cancer patients, and frankly, it would be very robust just for social freezing also. It sounds extreme, but why not? We've had very sophisticated women who are very busy in their life. They don't have time to do ovary stimulation. They just want to remove an ovary and freeze it, save their other ovary. And the studies from Japan show that it won't be any less fertile because of that. I know that's extreme. We have IRB for it, but it's a very reasonable thing to do. In fact, Klaus Anderson says that even is a way of preserving them from menopause until they're 100 years old. But also, now we figured out what it is that controls ovarian longevity, and it's simply tissue pressure, and it's the rotation of the nuclei of these eggs when they're under high tissue pressure in the ovary cortex that makes them dormant. And in fact, that may be the secret to longevity of all of our stem cells all over our body, because it occurs everywhere, nuclear rotation under mechanical stress. And so athleticism, by the way, and working out may very well add to your longevity because it'll cause nuclear rotation because of mechanical stress. But that's a whole nother subject. But also now we have a method where we get 2 for 1. One procedure, remove the ovary without any delay for the cancer patients, and you also can get M2 oocytes. The IVM is remarkably robust, never would have guessed it, but it's the way veterinarians have been achieving M2 eggs for many, many decades. And it's just clinicians have fooled around with other methods that just interfere with the natural in vitro maturation. Once you remove the follicle from the ovary. So, okay, I'm not sure technically what to do now, but I'm ready to answer questions.
Sherman, thank you very much for a very, very interesting lecture. I have a few questions, but most importantly is the question regarding the possibility that you and your team will have a course, a very short course on the internet, like giving a recipe how to do an IVM, because you know that many people try to do an IVM and it's not very successful in every lab. And this is actually the key issue regarding IVM, how you do it properly and how you do it right. So if you are willing with your team to have a short course, a video course of IVM, we'll be very happy to have it on the internet.
Oh, that would be great. Our team would be very excited about doing this. The only proviso, you probably heard it in my talk, is I want to make sure that I'm not the originator of this, that Klaus Anderson gets the credit for it. But we do it very well, and we'd love to give a course on it.
And the other thing is, which is quite important, when do you decide to vitrify egg or ovarian tissue? Is it age? Is it a disease? Is it a time limit? When do you decide how to consult your patient? How do you decide how to consult your patients?
Well, I think that's the important question really for us clinicians. If the woman has cancer and she's terrified and she wants to get on with her treatment and she and her oncologist really don't want to delay treatment, then it's just a no-brainer that we just take out one ovary, leave the other ovary intact, and we get ovary tissue. And by the way, there's been no cases of transmission of cancer yet from ovary transplantation. We get the tissue, plus we get the M2 oocytes, and she can 3 days later start her cancer treatment without any hesitation. So that's a no-brainer. The question is, if the oncologist says, well, we can give you a month safely before we start treatment. Well, we all know that it's safe in those cases to do random start stimulation and get stimulated eggs, and can certainly do that. And so the question is, what does that ovary tissue look like? Because we'll want to take the ovary out when they're done with their random stimulation, with their random start, because you definitely don't want to just rely on one cycle of IVF stimulation. You still want to get ovary tissue. So we've looked at that. And although the media looks awful, I mean, it's hemorrhagic and it's terrible looking. It's awful looking in these cases. And I don't have these slides for you in this talk, but I can give them in another talk. Although it looks terrible, the cortex is just fine. And so we can get primordial follicles and good cortex even in those patients that had the time to do one stimulation cycle. Now, what do you do about just the women that want to preserve their fertility? Unfortunately, usually they're 38 or 40 years old and they want to preserve their fertility, and they don't think about it when they're in their 20s. That decision they have to make based upon how much time they want to have available for doing 3 cycles or 4 cycles of egg retrieval versus just one 10-minute outpatient procedure removing an ovary. And I will tell you, very sophisticated patients, doctors, lawyers, CEOs, these women would prefer just to have an outpatient procedure, get their ovary frozen, do the IVM, and leave it at that, because the data from Japan is overwhelming that you do not reduce their fertility by taking out an ovary. So that'd be those would be my scenarios.
Thank you again. Thank you for being with us on this IVF Worldwide Platform webinar. And I would like to remind the audience that your email address will be on the screen, and you will be able and willing to answer any questions during the next 48 hours. So again, thank you very much for being with us today.
And thank you to everyone.